Okay, so chapter 6 is our thermochemistry one. And so the first one that we're going to try to focus on is our calorimetry. Now, calorimetry is what we're going to use in a lot of different cases to kind of measure the energy related to a process. Now, in this beginning part, our calorimetry is focusing on our heat change. And so remember that the heat energy is given by this equation, Q equals what we call MCAP. And so that's the mass of the material that's changing its heat, the specific heat capacity of that material, and then the delta T, or that change in that temperature. And that change in that temperature, normally we want that in either Kelvin or degrees Celsius, depending on what our specific heat capacity is in. We want to get those to match. The other part is, remember that delta T is always your final temperature minus your initial. So let's take an example. Water has a specific heat capacity of 4.184 joules per grams degrees Celsius. This means that it takes 4.184 joules to heat 1 gram of water 1 degree Celsius. So if we have 10 grams of water, how much energy will it take to heat it 1 degree Celsius? So that means that we're looking for Q. We're looking for our energy. Our mass is going to be 10.0 grams. Our specific heat capacity is 4.184 joules grams degrees Celsius. And our temperature change is 1 degree Celsius. Now, if we get that lined up correctly, you can see that our units should cancel, grams and grams, degrees Celsius and degrees Celsius. And so we're going to end up with joules. And so our answer should be 41.84 joules. Let's look at a little more involved process here. This time, we're going to find the energy needed to heat 30 grams of water from 10 degrees Celsius all the way up to 50 degrees Celsius. So we're still looking for Q, but this time our mass is going to be 30.0 grams. Our C is still the same, 4.184 joules per grams degrees Celsius, because it's still the same material. But our delta T is going to be different. So it should be our final temperature, which is the 50.0, minus our initial, which is the 10.0. And so we get a delta T of 40.0 degrees Celsius. Now, it is important that you do your final minus your initial, so that way your Q gets the correct sign. In this case, we should be heating, and so we should be gaining energy, right? So we should be putting in heat. So that's why it's going to be positive. If we were cooling, let's say we're going from 50 degrees Celsius to 10, then our final would be the 10. Our initial would be the 50, and so our delta T will be negative 40. So you just want to make sure that you're paying attention to which one is your final and which one is your initial for your temperatures. So we plug this back into our equation. Our mass is 30.0 grams. Our C is 4.184 joules per grams degrees Celsius. And our delta T is 40.0 degrees Celsius. We multiply those together. And we get 5,020.8 joules. And if we look at our significant figures, we should have 3. So 5,020 joules. Okay. And so that's what we're looking for these type of problems we're trying to solve for that Q. Now, a standard problem might be when we have a pot of water, which is 2.5 liters of water, initially at 25 degrees Celsius, and we heat it to boiling. And so we want to know how much energy is needed to heat that water. So it gives us some different information here. So we can imagine that we have this pot. It's on the stove, so we're adding some water to it. Now, we are looking for heat, Q, and so we should be thinking MC delta T. We know that it's water, so that should be our C is 4.184 joules per grams degrees Celsius. We know our delta T, our final is 100 degrees Celsius minus 25, which is our initial. What we don't know is our mass. So we want to try to piece that together. So we know that our mass is related to our volume by our density. So if we take our 2.5 liters and we multiply that by 1,000 milliliters to 1 liter, and we change our density of our water, 1.000 grams per 1 milliliter. Now, that wasn't only one significant figure, but I should update that and give you some more. And so we get a value of 2,500 grams of water. So now that we have our mass, we can update it over here, 2,500 grams. And so our Q becomes 2,500 grams, 4.184 joules per grams degrees Celsius, and the delta T is 75.0 degrees Celsius. Actually, it should just be 75 when we think about those significant figures in there. So 2,500 grams times 4.184 times 75, we get a Q that's equal to 784,500 joules. This is why boiling a pot of water takes so long, is because it's a lot of energy that you have to be putting inside of that. Now, when we think about the significant figures, we should just have 2, so it's really 780,000 joules. And now they want us in kilojoules. So remember that 1 kilojoule is 1,000 joules. So 780,000 joules should become 780 kilojoules. And so now we're looking at the amount of heat released when 175 grams of water cools from 100 degrees Celsius to room temperature of 20 degrees Celsius. So we're still looking at our Q here. Now this time our mass is going to be 175 grams. Our C, because it's water, is still the same. And the delta T this time, we don't want to start with the 100. That's going to be our initial temperature, not our final one. So we really want 20.0 degrees Celsius minus 100. Now the reason why is that this is going to get our heat to properly reflect whether we're gaining that heat or giving away that heat from the system to the surroundings. So the Q that we're concerned with is the Q for our system, not how much heat is being gained by our surroundings. So our mass is 175 grams. Our heat capacity is 4.184 joules grams degrees Celsius. And our delta T is negative 80 degrees Celsius. So 175 times 4.184 times negative 80. And our Q of our system becomes negative 58,576 joules, or with our 3 significant figures, negative 58,600 joules. So the fact that they tell us that it's released, that lets us know that it should be a negative, and the fact that our negative sign lines up with it, and that's good. The wording of the question, we would probably also accept just 58,600 because it's saying released, and so we already imply that we're losing that heat. But if it would just said, what's the heat related to this process, then we would want to make sure that we include that negative sign in there. And so that's our beginning ones. But it doesn't always have to be water that we warm up or cool down. It can be any other material. So let's take copper metal, for example. Copper metal has a specific heat capacity of 0.39 joules per grams degrees Celsius. And so when we compare that to water, is it easier to heat up are harder to heat up. And so the specific heat capacity tells us the amount of energy need per gram per 1 degree Celsius. And so copper is going to be easier to heat because it requires less energy. If we have 10 joules of energy, we can get that 1 gram of copper to go up by, no, we have to do that math. 10 divided by 0.39. 25 to 26 degrees Celsius. Whereas water, if we have 10 joules, we would divide it by 4.184. We can only get up to go about 2 to 3 degrees Celsius, right? So copper is a lot easier for us to heat up. So in this case, our equation still seems the same. It's still Q equals mc delta T. Our mass in this example is going to be 5.20 grams, but our C has changed. It's not going to be this 4.184. It's going to be the 0.39 joules grams degrees Celsius. Our delta T is still 100 because that's our final, minus 20.0 to give us 80 degrees Celsius as a change. So plugging that in, we get our Q is going to be 5.20 grams, 0.39 joules grams degrees Celsius. And our delta T is 80 degrees Celsius. So 5.2 times 0.39 times 80, and we get 162.24 joules, or 160 joules once we look at our significant figures. So significantly easier for us to do the heating of that copper compared to that of water. And so let's compare that. Let's say that we have the same amount of energy. So in this case, we have 300 joules of heat energy. We're going to use it to heat up 5 grams of copper metal and a separate 5 grams sample of water. Both of them are going to start at 10 degrees Celsius. And so we want to find the final temperature of each sample. So final temperature, that's our TF. So if we look at that equation, our heat of our copper is going to be the mass of the copper times the heat capacity of the copper times your final temperature minus your initial. And so our initial is going to be the same in this case. It's going to be 10.0 degrees Celsius. For our water, that's going to be the heat of our water is equal to the mass of the water, the heat capacity of the water. We'll get it to its final temperature minus its initial, 10 degrees Celsius. So in both examples, we are going to put the same amount of energy. So our Q is going to be 300 joules for each. Our mass is going to be the same at 5 grams. But our heat capacity is going to be different. For copper, it's 0.39 joules per gram degrees Celsius. And so we're going to use that to find our final temperature if we start at 10 degrees Celsius. Water, we'll go ahead and update that as well, 300 joules. Our mass is going to be 5.00 grams. Heat capacity, 4.184 joules grams degrees Celsius. Our final minus our initial temperature. So we can consolidate those terms a little bit. We can take 5 times 0.39. That gives us 1.95. Wrong color there. Joules per degree Celsius. And our TF minus the 10. We can consolidate the other side. So this becomes 300 joules, 20.92 joules over degrees Celsius. And from there, we want to take that 300 and we can divide it by 1.95. And so we can get our final temperature minus 10 degrees Celsius is equal to 153.85 joules. And so all I did was I moved that 1.95 to the other side, so that way I can group those terms. So I'm taking 300 joules, I'm dividing by 20.92. That's giving me 14.34 degrees Celsius. Yeah, that shouldn't be joules anymore. That should also be degrees Celsius. And that's our final minus 10.0 degrees Celsius. And so now we just need to add in that 10 to get our final. So that's 24.34 degrees Celsius. This one becomes 163.85 degrees Celsius. And you can see that there's a big change in the final temperature that we can reach for each of them. Water would barely get up to like room temperature, and our copper is way past the boiling point of water. Right? So there's a big change in that. Now remember that when we talk about these terms, there's a sign that gets associated with them. Negative Q is always the heat that's being released because we're losing that heat energy. A positive Q means that you're absorbing that heat, and so that means your system is absorbing it from the surroundings. If a positive Q is related to our system, and if we're gaining heat as a system, then our surroundings must be losing that, and so it's going to have a negative. So it should always be our final temperature minus our initial. If something is getting hotter, then it makes sense that heat's being absorbed, so our final should be higher than our initial, and that gives us a positive delta T. If something is getting cooler, then that means we have to be losing heat, so that heat is going to be released, and so our final should be less than our initial to give us a negative delta T. So let's say that we mix 90 grams of hot water with 10 grams of cold water, right? So the hot water is at 90 degrees Celsius, the cold water is at 10. And so we're trying to find the final temperature. So what we want to do is we can set up our equation. In this case, they want to figure out the energy released by the hot water. So that's going to be our Q of our hot is going to be the mass of our hot, 90.0 grams, heat capacity, 4.184 joules, grams degrees Celsius, and the delta T, which is our 90.0, oh, not our 90, that's our initial, which is our final temperature. In this case, they want it to be X minus 90.0 degrees Celsius. For the heat absorbed, so that's for the cold, that's going to be 10.0 grams, 4.184 joules, grams degrees Celsius. And this one should be our X minus 10.0 degrees Celsius. So now if we imagine this, let's say that we had one cup, which is our hot water, and we had another cup, which is our cold water. When we mix those together, that heat exchange is going to happen. And they're going to meet somewhere in between for the final temperature. That means that the heat that's released by the hot is going to be equal to the heat that's absorbed, except that it's got this negative sign there. So when we're ready to put these two equations together, we know that Q hot should be equal to Q cold, except for it being the negative. Because the heat gained by the system has to be lost by the surroundings. Sorry, the heat lost by the hot has to be gained by the cold system. And the heat gained by the cold must have been lost by the hot. So they are equal, just opposites. So in this case, when we're putting them together, we can have 90.0 grams, which is our Q for our mass for our hot, 4.184 joules, grams degrees Celsius, X minus 90.0 degrees Celsius, being equal to negative 10.0 grams times 4.184 joules grams degrees Celsius and x minus 10 degrees Celsius. So I have to have that negative sign in there. It doesn't matter what number I put the negative with, just as long as that whole side gets a negative. So if we're ready to solve for x, we can go ahead and remove our heat capacities, right? I can divide both sides by 4.184. That gives me 90.0 grams times x minus 90.0 degrees Celsius is being equal to negative 10 grams times x minus 10.0 degrees Celsius. I'm going to move that over here so that way we can have a little bit of space. So I can consolidate my terms. I'm going to take my negative 10, I'm going to multiply that by x, so negative 10.0x. Negative 10 times negative 10, that's positive 100.0 degrees Celsius. Actually, it wouldn't just be degrees Celsius, it'd be degrees Celsius grams. Our other one would be, on the other side, is 90.0 grams x minus, and then 90 times 90, (8,100), and so that's grams degrees Celsius again. All right, and so we want to get our x's onto one side. So if I consolidate our x terms, I'm going to bring them over to the left, so that becomes 100 grams x. And I'm going to bring my degrees Celsius to the other side, so this becomes 8,200 grams degrees Celsius. We divide both by the 100 grams to get rid of that. And that's going to leave us with x is being 82 degrees Celsius. Which makes sense because it's halfway, or not halfway, but it's between our 10 degrees Celsius, which is what our cold started with, and the 90 degrees Celsius, which is what our hot started with. So that's a good sign. And so that's what we were looking for. And so this is kind of how calorimetry works. Now, it doesn't always have to be water. Sometimes we can get a lot of different types of things. So let's say that we have 175 grams of hot aluminum. And we're going to drop that into an insulated cup that has 40.0 milliliters of ice cold water. So water at 0 degrees Celsius. We want to try to find the final temperature X. So let's look at our aluminum. Our aluminum, well, that's going to be its mass, so 175 grams. It's got a specific heat capacity of 0.900 joules grams degrees Celsius. We don't know its final temperature, TF, but we do know its initial was 100. For our water, its mass is going to be 40.0 milliliters. So we have to turn those milliliters into grams. We know 1 gram is 1 milliliter, so 40.0 grams. Its C is 4.184 joules grams degrees Celsius. We don't know its X, or its final temperature, so final, but we do know its initial was 0. Now we need to go ahead and put those together. So our Q of our aluminum is going to be equal to the negative Q of our water. We know Q of aluminum is 175 grams times 0.900 joules, grams degrees Celsius, and our TF minus our 100. We know our water is going to be negative 40, right? Because we want to keep that negative sign, 40.0 grams, 4.184 joules over grams degrees Celsius, and our TF minus 0. Now this time we can't just remove the specific capacities because they don't match. So we have to kind of consolidate them. So I'm taking 175 times 0.9. And so I'm going to basically combine these two terms here into one number. And so that becomes 157.5 joules degrees Celsius, TF minus 10.0 degrees Celsius. My other side, negative 40.0 times 4.184. This becomes negative 167.36 joules degrees Celsius times that TF minus 0.00 degrees Celsius. Now I'm going to go ahead and disperse my capacities to my, my final temperature and my initial. So as an example, I'm going to take this 167 or negative 167.36, and that's going to give me negative 167.36 final temperature minus, and then 0 times 167.36. That's going to give me 0 joules. And that's going to be equal to 157.5 and then you multiply that by negative 10. On the other side, I can bring my terms together. So I'm going to bring both my final temperatures over onto the left-hand side. So 157.5 plus 167.36. This becomes 324.86 joules degrees Celsius for my final. And I'm going to bring my other term over to the right. So this becomes positive 1575 joules. So 1575 divided by 324. And our final temperature is going to be 4.848 degrees Celsius. So that's kind of what we're looking at to do there. So just remember that when you're setting it up, pay attention to your negative signs. Your math can get a little bit messy at different points, but as long as you're keeping track of your correct signs, then they're going to work out. Also, it's always a good idea to check at the end. And so when we look at our final temperature, it means that our cold water gained some heat to get to that final temperature. That looks good. It means that hot water lost some heat as it got down there. So that looks good. And so that all works out. So that's very good for us. Okay. Now, there's somewhat some confusing terms that get introduced here. And so we just want to make sure that we're paying attention to them, right? So one of them is that 74.8 joules of heat is required to raise the temperature of 18.69 grams of silver from 10 degrees Celsius to 27.0 degrees Celsius. And so it wants to know what is the heat capacity of the silver sample. And remember, its units for heat capacity is joules per degree Celsius. That value is useful, but only for this specific sample of the silver. There's a different term that they also introduced, which is what is the specific heat capacity of silver, and that's joules per grams degrees Celsius. This one's useful because it is used for any sample of silver, as long as we know the mass. So sometimes the specific heat kind of gets used back and forth between these. What we really want to be thinking about is heat capacity is for a specific sample. Specific heat or specific heat capacity is for that material. So the heat capacity of this silver sample, well, we know that Q is 74.8 joules. We know that its mass was 18.69 grams. We know that it went from its delta T of 10.0 degrees Celsius to 27.0 degrees Celsius. So its mass is 18.69 grams. Its delta T is going to be 27.0 minus 10.0, so 17.0. And what we don't know is its C. So when we're looking for this, we can try to determine its heat capacity, and we just need that for joules per degree Celsius. So instead of plugging into Q equals MCAT, because that C in MCAT is actually a specific heat capacity, we just need to take those joules, and if we divide that by our 17.0 degrees Celsius, we'll have the specific heat capacity for that specific sample, we'll have the heat capacity for that specific sample of silver. On the other hand, if we want the specific heat capacity, now we need to take that heat, we need to divide it by its mass, 18.69 grams, and its temperature change, 17.0. And so now 74.8 divided by 18.69 divided by 17. Now we have its specific heat capacity, which is a lot less, 0.235 joules per gram degree Celsius. So remember, heat capacity is for a specific sample, and it doesn't involve the mass of it. Instead, it's saying for this object, this is the amount of energy to raise it 1 degree Celsius. That's handy if we're going to use that same object over and over again. The specific heat capacity, that's for a material, and that one does take the mass into account, and so that's our joules per gram degree Celsius. And that's really useful because we could use that for any type of that material. So we can use it for any sample of silver, but we do have to know its mass. Okay, I hope that helped.